Okay, wonderful. It's so good to see so many familiar faces, so many smiling people from here and from afar. I was just so happy. I'm so happy to be back here. I spent 6 years here, as Gus was saying, as a postdoc and an associate research scientist. So I'm just thrilled to be back and to tell you what I've been up to. So because I have no expectation that anyone knows anything about black holes, and you're here because you think black holes are cool, and that's also why I'm here. So I'm going to walk you through the black holes that we'll be talking about today. So I'll start with primordial black holes. These may have formed in the early universe. These are extremely complicated to explain. It also sort of depends on who you ask as to what exactly the definition, but these are basically objects that are in the very early universe that could have been formed from quantum fluctuations that just kind of formed this really dense point that turned into a singularity and then is a primordial black hole. So it was never a star. These are very cool. Stellar mass black holes are what LIGO routinely detects these days. These are like a few solar masses to maybe 50 or 60 solar masses. Then you kind of get into weird definitional areas where, is it an intermediate mass black hole or not when it gets up closer to 100? But stellar mass black holes are the stuff of the press releases for LIGO. And you've probably heard a lot about these guys. Intermediate mass black holes are really new to the game. So these form either also in the early universe, or they can be formed through hierarchical mergers. That means that you have one black hole merging with another black hole, and it gives you something that's over 100 solar masses. And so this is an intermediate mass black hole. But my love, my one and only true love, well, one of them, I love you, baby, are supermassive black holes. He knows. I love supermassive black holes. And even supermassive is a kind of misnomer because there's baby supermassive black holes that are 100,000 to 1 million solar masses. And then there's the billion solar mass supermassive black holes. And you might tell from the enthusiasm in my voice that those are really what I'm excited about. So with supermassive black holes and looking for gravitational waves, the bigger the better. We want really big black holes because they rip up the fabric of space-time as they're merging with each other. And the gravitational waves that we look for from these supermassive black holes are so big that they're about the size of a virus divided by the diameter of the Earth, which is about 1 million times larger than what these guys make, right? Which is the fraction of the size of a proton. As Gus pointed out, LIGO has a very good PR machine. So every time I have a little factoid I can share with you about my black holes, I really try to drive it home. Okay, so again, I'm assuming very little prior knowledge, and I hopefully can teach you something about black hole anatomy. So black holes have something in the center that's a singularity. Singularity, no one really actually knows what it is. It's kind of where general relativity and quantum mechanics somehow merge and where our understanding of the equations that govern both of these regimes completely breaks down. The more sophisticated audience member may protest and say perhaps it is a quark gluon plasma. Perhaps you are right. Nobody knows. Right now there's no way of accessing that information. At the center there is a singularity, and it may or may not be a thing. It might be a point of infinite curvature of space-time. It might be a ball. It's super unclear exactly what that is. And then for the purposes of this talk in particular, and to bring you up to speed with what's new with supermassive black holes, is this accretion disk. Now, the accretion disk is what happens when you have a star or other material that gets close to the black hole, and it gets torn up by the black hole. And so instead of, sometimes it can just be on a crash course and dive right in, it normally has some sort of orbit like this around the black hole, and the black hole tears it up, and this hot disk of gas is normally what we can actually see when we talk about seeing black holes with any kind of electromagnetic observation. So that's X-rays, optical light. Whenever someone takes an image of a black hole, of course, they're not actually taking an image of the black hole. They're taking an image of some sort of electromagnetic radiation, which is light, that's around the black hole. Okay, so now we have gas around the black hole. the black hole with the mystery inside, like a Kinder egg. And then, but those are illegal in the US, I think now, right? Yeah, guns are fine. Okay, so then you have your innermost stable circular orbit, and then you can have really strong magnetic fields, and you can launch jets, relativistic jets. And so these jets are also visible with some black holes all the way out to the edge of the universe. So this is really what a black hole would look like if we could see one. And it's true for all black holes. One beautiful thing about black holes, and any simulator in the room will tell you, is that they are scale-free, which means that black hole physics works for black holes at any scale if you believe Einstein's theory of general relativity. And so everything I told you will happen for all black holes, but not all black holes have these disks around them. Some of them might just be completely dark, in which case you can see them through lensing effects, for example. And the physics is the same. Not all of them have jets. The ones that do are pretty awesome. Okay, so it's really funny, I think, these days that we take black holes for granted in a certain way. When I was a kid growing up and I discovered that black holes were a thing, my science teachers were like, well, we're not really sure that black holes are real. I'm not sure you can do your science project on black holes. And I was like, excuse me, but have you not heard of Cygnus X1? And then she was like, I have no idea what you're talking about. And so I decided to look up this original paper to remind you all how new black holes are to the literature, right? Some of you might have grown up without knowing that black holes were real at all, just kind of like I was born before we knew that extrasolar planets existed. Right now, everyone takes it for granted that there's planets around other stars. And of course, it makes a lot of sense. And if you're a physicist, then you might also believe that black holes made a lot of sense. But in fact, it's actually quite difficult to find black holes. So the first evidence for the stellar mass black hole was in something called an X-ray binary, where there was a black hole and a star around it, and there was X-rays that were detected from the system, right, from the accretion disk and from this interaction. And this was published in 1972. But even in 1972, Kip is like, I think that's real. And Hawking was like, I don't know, man. I don't know if that's a real black hole. And he's like, do you want to bet? And he's like, sure, how much you want to bet? And so in 1972, these two made this bet as to whether or not Cygnus X1 was a real black hole. And Hawking only conceded in 1990, right? That's a long time. The subject of their bet is still displayed outside of Kip's office. And if you know, you know. Some of you know. So he conceded in 1990, Cygnus X1 has a black hole that is about 20 solar masses. So it just goes to show, this is really new. So in 1990, it took someone who had dedicated his entire career to studying black holes, to have another famous cosmologist concede that they were even real. And that's not so long ago, right? We still all know music from the 90s, right? There's a lot of things happening in the 90s. Okay, so Kip then went to give us the movie Interstellar with a supermassive black hole that he calls Gargantua, which I think is really, really awesome. And so Gargantua is an example that I think we're all familiar with now of a supermassive black hole. And so here's a more dynamic version of my little black and white figure, the accretion disk around Gargantua. What's really fun here is that you can see lensing effects, right? So some people wonder about this eyebrow that goes up around Gargantua, and they think that somehow the gas is going up and over or down and under. But this is actually just a lensing effect. You're actually seeing the accretion disk behind the black hole flipped up, and it kind of looks like a halo. So you can see everything happening as it's going around, which I think is really, really awesome. So supermassive black holes are different beasts than stellar mass black holes. There hasn't been enough time in the history of the universe for enough stellar mass black holes to merge to give you a supermassive black hole. So they are born big. And if any of you are following the breaking news in astrophysics, you might have seen the article about little red dots that appeared this week in Nature, about how these little red dots that the James Webb Space Telescope has found may indeed be these nascent supermassive black holes from the very early universe. But nobody knows really how these really big black holes were formed. So this is something called a merger tree. And basically what happens is that at some point in the early universe, supermassive black holes formed. Now, my colleague at Yale, Priya Natarajan, is really famous for her theory that there was a direct collapse of a gas cloud into a supermassive black hole. And it's also possible that there were some early stars that formed and lived fast and died young and created black holes that eventually merged to give you some supermassive black holes early on. We can't really tell right now what these seeds were for supermassive black holes. And I think it's really cute that we call it supermassive black hole seed theory, but that's what it's called. So the black holes find each other and merge and merge and merge and merge, and then today create supermassive black holes, which are the ones that I'm interested in. I'm also interested in this merger process, because when two supermassive black holes merge, they create giant gravitational waves. And again, giant, I must warn you, means 1 part in 10 to the 15, or 1 part in a million billion. So those are the biggest gravitational waves in the universe. Okay, so you may have heard about supermassive black holes in the news also from some recent Nobel Prizes. Andrea Ghez and Reinhard Genzel shared the Nobel Prize with Roger Penrose for Sagittarius A star, the supermassive black hole at the center of our galaxy. And so it's not a party unless there's an equation on the board, right? And I've spoiled you guys. Now everyone get out your pens. And you can, if you're a relativist, you can do this in dimensionless units. Things are much, much easier when one solar mass is 4.9 times 10 to the minus 6 seconds. So anyhow, what they did is that they looked at the center of the galaxy where Sagittarius A star is, and they proved that there had to be a supermassive black hole there. And they did that by using very simple math, basically using Kepler's third law. And they observed the stars that were going around nothing, right? They were going around this massive body, and the more times that you measured one of these closed orbits, the better your estimate on the mass was. And eventually they had so many good measurements of this that they could tell you that there's a supermassive black hole in the center of the Milky Way that's about 4 million solar masses. And that is pretty impressive. So what's better than one supermassive black hole? That's right. Thank you, audience. 2 supermassive black holes. And my friend Scott Noble's amazing animations of these supermassive black holes. And so here, this is paused in the middle of an animation, and then the camera is being flipped up and down to show you, again, these really cool lensing effects. This is really just a break for you after seeing a lot of math to give you the sense that things are still awesome and you don't need to calculate anything for real right now. It'll be easier, though, afterwards, after you have a few glasses of wine. I find that's typically true. OK, so 2 supermassive black holes are what I'm after. And the way that we look for them is with pulsar timing arrays. So we have right now the famous LIGO experiment. And LIGO detects stellar mass black holes in something called with the audio band. We call this the audio band because if your ears were gravitational wave detectors, you'd be able to hear the gravitational waves as they merge. They make a sound that goes whoop, right? And that's called a chirp. So it starts at low frequency, and then it goes to high frequency, and it really goes whoop as it's merging. OK, so in the millihertz band, you have the LISA detector, and that will launch in about 10 years from now. And this will detect the mergers of baby supermassive black holes, which they're very cute, right? They're not the ones that I'm looking for, but they're very sweet. They're 10 to the 5 to 10 to the 6 solar masses. And they are the black holes that eventually merge and grow to give you the supermassive black holes over here. Now, these supermassive black holes are the 10 to the 8 to 10 to the 9 solar mass black holes, so about 1 billion solar masses. And those are so big that you can hear the rumbles in the fabric of space-time that they create tens of thousands of years before they start merging. So whereas you're likely familiar with the whoop transient signal, and then all the telescopes trying to find where the thing went whoop in the sky and everyone's looking for it, these supermassive black holes are very slowly evolving. And again, their gravitational waves are so big that we can find them tens of thousands of years before they merge. And they're in our detector band potentially for millions of years. So these are not transient. These are transient, they come and go, and there's lots of them. But these are a gold mine. They're more difficult to find, but once you get them, they just keep producing. And so what my work is focusing on right now, now that we have evidence for a gravitational wave background, and I'll tell you what that means, is finding the individual supermassive black hole binaries. So before we go, you may notice that there are two Mingarellis that have created this figure. So this is Papa, A.B. Mingarelli, and then this is me. And basically what happened is that it was Christmas dinner, and there was, again, a lot of wine. And I was like, Papa, I just solved this equation using Python. Look at my notebook. Isn't it beautiful? And he was like, I don't know what you're doing, Chiara. This is crazy. Like, surely this is just a straightforward application of the Riemann-Lebesgue lemma. And I was like, I don't know what that is, Papa. And he was like, he's a mathematician. And he was like, I taught you that in your second year calculus class. How could you forget that? And I was like, I'm a failure as a mathematician, Papa, forgive me. And he was like, well, we can prove this, and we can prove that everything that you're doing in Python just is like 3 lines of math. It was more like 10 lines of math. But he was right. It was a straightforward application of the Riemann-Lebesgue lemma. So we wrote a paper, and it's a math paper, and I wanted people to read the paper or cite it from time to time, so I made a nice picture to go in the paper so that other people would want to use the figure and then cite the paper. And that is exactly what happened. It's the only way to get people to read this paper. Okay, so I think I said everything I wanted to say. Let's move on. Another animation. This one is so old that it's cool again. Someone like Abby, who's 20-something, would make this and feel like it's very kind of retro and awesome because it looks like it was made in the 90s, and it was. So each galaxy has a central supermassive black hole. And when the galaxies merge, their supermassive black holes merge. And so here we have 2 of my favorite, billion solar mass black holes that are creating these gravitational waves, which is this space-time fabric that's rippling away from you, towards you. Direction is relative. So these ripples are coming towards us here in the Milky Way galaxy, where we're timing millisecond pulsars. So millisecond pulsars are these dead solar cores, and they rotate around at the speed of a blender. Now that's pretty impressive for something that's about 2 times the mass of the sun and is the size of Manhattan. Right? So take the sun, compress it into the size of Manhattan, put it in a blender, and you get a pulsar. So these are really extreme astrophysical objects. And it's, again, one of those things that you would think is nonsense. It doesn't make sense. And these were discovered in 1982, which I hear was an excellent year. So these pulsars are ultra-stable clocks, and their signals are advanced and delayed by something like 100 nanoseconds over a decade by these gravitational waves. And again, this is just another way of telling you that it's 10 to the minus 15. So these advance and delays are what we use to infer the presence of gravitational waves. So it's like you took LIGO, and then you took a laser, and you put it somewhere a kiloparsec away, which is about 3,000 light years, and it just sends signals in one direction. So when we look for this, we don't look for signals from just one pulsar, but from an array of pulsars. And the array is important because a lot of stuff is in this interstellar space. We're in the Milky Way, so between us and the star. It is interstellar. Nice. Okay. And so that can mimic a gravitational wave signal. So we have to have a lot of pulsars, and the only signal that's correlated between all of these pulsars is going to be this gravitational wave signal. The noise at the pulsars, for the experts in the room, is not correlated, but your signal is. So the more pulsars you have, the more you can beat down the noise and build up your signal. So this is the overall idea of a pulsar timing array, looking for small shifts in these ultra-precise clocks that are coming in from thousands of years away. Now, I told you earlier that these supermassive black holes take a really long time to merge. So some of you are probably thinking, aha, Well, that means that you can't detect one because at any given point in time, there's probably millions of them that are simultaneously merging because those mergers take so long. And if you thought that, you are right. So the first signal that we found was evidence for this random or stochastic gravitational wave background. So the background is the superposition of hundreds of thousands to millions of individual binary systems. So here you have your two very massive black holes cozying up, creating ripples in the fabric of space-time. And an artist did a really nice job of trying to show you what that would look like if you could see a stochastic background of gravitational waves. So stochastic just means random. But something really interesting happened with the measurement. We know that there's a gravitational wave background, and I'll tell you why we know that in a few seconds, but we don't know what's sourcing it. So I am a big fan of supermassive black holes. I feel I've been very straightforward about that. But other things can create low-frequency gravitational waves. Cosmic strings, right? Cosmic string networks in the early universe. They might be creating gravitational waves. Greg can tell you all about cosmic strings if you ask him nicely, or maybe give him a few glasses of wine. But basically, you have these long, if you even look at this analog laser pointer, if you look at this line here, imagine that this is almost infinitely dense. And then imagine that it now, it formed in the early universe. And what happens is that it can interact with itself and it can create a loop. I'm not going to try to bend this. That would be a disaster. But imagine this creating a loop, and then the loop pinches off and starts radiating gravitational waves. It's vibrating and it's radiating gravitational waves. That is a thing that can happen, apparently. And that can create a background of gravitational waves. The only way that we can tell what's sourcing the background is to try to find, one of the original sources, like an individual binary. Or we can tell by the way that the amplitude of the background changes as a function of frequency. So we're looking for that. So the thing that we're looking for in particular, the way that we know that there's evidence for this gravitational wave background is through this blue line here called the Hellings and Downs curve. So I'm going to show you this animation that one of my undergraduates made to try to illustrate where this comes from. And the paper that this is an animation for, we submitted this morning. So this is really exciting. There's an APS editor here right now. This is very good work, very high quality work, Matteo. Okay. So what we did is that in this animation, I show you point by point how you create this correlation function. This is called the Hellings and Downs curve. And I'll play this a few times because it can take a little bit of thought to get it right. So here I have individual supermassive black holes that are popping up one at a time. And the blue curve is the thing that we predict theoretically. And the red curve is the thing that I'm calculating point by point by point. I'm going to go over this again. So this is like a freeze frame of just, something like a dozen binaries. You can see after only 12 binaries that the blue curve is really close to this red one, which is the average of all of them. And that was really the insight into this paper, that we can build up the background point by point, and that individual sources make correlation functions. And when you average them together, they give you this Hellings and Downs curve. So you can see, again, as you build up point by point really slowly, you get this curve. And this curve, which is now here depicted by the black line, is the thing that we found in 2023. So this was evidence for an isotropic gravitational wave background. If there were no gravitational wave background, there would be no correlation. But what we found is about a 3.5 sigma detection of this Hellings and Downs curve. And so that's how we know that there is a stochastic background. But this curve is completely generic. It doesn't tell us that it's from supermassive black holes. This could be made by our friend, the cosmic strings. I think there was an episode of Star Trek with cosmic strings when I was a kid. So it's very cool and fascinating. Okay, so to find this Hellings and Downs curve, this 2-point correlation function for the experts in the room, we needed to look at 68 pulsars with nanograv And that formed 2,211 pulsar pairs that were binned here. This is no small feat. The data were collected for 15 years. So 15 years of people going to telescopes, timing these millisecond pulsars every 2 weeks. When I was an early postdoc, they started switching to doing more remote observing. And anyone that's done radio observations, if there's any astronomers in the room, will know that there's really cute sounds that different telescopes make. Some of them chirp at you. Some of them sound like parrots. The ones in Australia make parrot noises. And they give something for like the person who's observing the data to keep them awake or to keep them entertained, which I think is really sweet. It's a thoughtful touch. So we had 67 pulsars of time spans that are greater than 3 years. And I know that a lot of you in the room are Bayesians. And so instead of talking about, frequentist statistics, if you don't know what that means, that's a sigma thing that I said. There's a Bayes factor of 900 to 1 for having this Hellings and Downs curve. So a Bayes factor are just betting odds, right? I would give you odds of 900 to 1 that this correlation pattern exists in our pulsar data. So I find that quite convincing. I think other people do too. Okay, so far you've learned that supermassive black holes are at the centers of massive galaxies. When galaxies merge, their supermassive black holes merge, they make the biggest gravitational waves ever, and those are still very small. We search for the gravitational waves with pulsars because we look for advance and delays in their arrival times at the Earth. And now we have evidence for a gravitational wave background, and we're pretty sure it's from supermassive black hole binaries. And that's a really fun thing, to think that the most vanilla, easiest explanation of the gravitational wave background is millions of simultaneously inspiraling supermassive black holes. I think that's pretty awesome. Okay, so how do we find these individual binary systems? If there's so many of them, maybe there's one nearby, right? Maybe we'll be really lucky. And so for the last 2 years, my students and I have been trying to figure out a way to find an individual binary. And of course, 2 years in the grand scheme of things is nothing. But what we did, I think, is really exciting. What's even more exciting for you, some of you are already sleeping, that's valid, is another animation. Okay, so in 2020, my colleagues and I wondered, what would we gain from having really narrow priors on some parameters in our searches for these individual binaries. And what that means is, why don't I stop pretending like I don't know where supermassive black hole binaries are? If they're supermassive black holes, they are in big galaxies. If there's 2 supermassive black holes, they will also be in a big galaxy because they came from big galaxies. So when they merge, they made a bigger galaxy, right? Okay, so let's just go look in big galaxies, one by one, and see what happens when we don't look over the whole sky and pretend like we don't know where we're looking. What happens if we just look under the lamppost and see what's there? So what we found is that for a nearby galaxy that improved our upper limits on the strain by a factor of 2. But if we knew the frequency, even to within an order of magnitude, we gained a factor of 10, right? That's 2 ways of saying 10. Just so that it's not confusing. But if we know the frequency to within a factor of 10, then we gain a factor of 10 in our sensitivity. And so I set out to try to find all of the galaxies that we knew of, that have a tracer that can tell us something about what the frequency is, because this is a huge gain. And so some of my colleagues who are maybe former students at NYU or worked with Andrew McFadden at NYU, developed this code called Sailfish, which is a GPU-based simulation. And these are 2 supermassive black holes. And you can see as they are inspiraling, there's this lump that's being created around them in this accretion disk. So now you're about to become accretion disk experts. This is a circumbinary accretion disk, because it's around the 2 black holes. And these are mini disks that are around the original black holes. And so there's a lump that forms, and you can see it kind of brightly coming out here towards the end of the animation. And this bright lump is the thing that we can actually see with telescopes. And because this bright lump is going around and circulating, you can actually, with the telescope, see galaxies that have these periodic light curves. And so if the lump co-rotates with the binary, it can tell you what the period of the binary is, and therefore the frequency, and then you can figure out what this frequency is. So we did that. We assembled 114 of these active galactic nuclei with periodic light curves, and there was no evidence for gravitational waves in any of them, except for in 8 targets that had Bayes factors that were greater than 1. Now, greater than 1 isn't really saying a lot, but these 2 certainly looked pretty interesting, right? So this one is called Rohan, for the student who found it. His name is Rohan Shivakumar, and he was an undergraduate working with me over the summer. I took these 114 galaxies. I gave each undergraduate 20 galaxies to look at and said, go, run the code on the cluster and come back and tell me what you find. And he was like, this one looks pretty cool. And it did. And then when we found the second one, are there any Lord of the Rings fans in the room? I mean, we had no choice. The beacons were lit, right? That's right. Okay, so what do we do with this information? Well, now we have to see, what do these low Bayes factors mean? They're very low. So something, a Bayes factor of 3 to 4 is just 3 to 1 or 4 to 1, betting odds. And to find the background, it was 900 to 1, right? So is this reasonable? And how do we figure out if this is the beginning of a detection or if it's just noise? That was really the point of this paper. So this is some eye candy for the Bayesians in the room that like a good corner plot. I know there's a few of you in here. So the red line here is your prior, and the black is the posterior distribution. Now, if there's no signal in the data, it'll just be, you'll recover your prior, right? And if there's something there, it'll make something spiky, and the spikier the better, right? You want to have a lot of your weight here above your prior. So this was exciting, especially for Forrest and Bjorn, who made these 2 plots. So Rohan is at 21 nanohertz and Gondor is at 14 nanohertz. And they still have low Bayes factors, but these corner plots were very exciting because this is a measurement of a supermassive black hole binary candidate's mass. It is about 10 to the 10 solar masses, which is very big and very exciting. Now, there were 114 targets. So then you have to ask yourself, what are the chances that just randomly some of the noise looks like a supermassive black hole binary? And so this was a lot of the other work that we did. We tried to figure it out. So when we put Rohan and Gondor in the context of the greater, candidate landscape, we found that they, look pretty normal. There's nothing, sticking out or strange about them. We also found that doing this, per frequency targeted search overall improved each candidate strain by a factor of between 2 and 13. The median is about 3. So we still are doing better, but not as well as we hoped. So the first study just looked at this one candidate galaxy, right? And we were spending a lot of time looking for frequencies because that would give us a factor of 10. But that was just for like this pilot project galaxy. And so my student, Forrest Hutchison, who at the time was an undergraduate, and some of you in the room know what that's like, he went away over the holidays and came back and said, I saw that your private partition on the computing cluster didn't have anything going on it. So I know that you only gave me 20 galaxies, but I just decided to run all of them just in case that was useful for you. And I was like, never leave me, Forrest. That is the correct thing to do. Yes, thank you. So that's how we found the other guys. Okay, so then you're trying to look for something like, well, is there some sort of overall improvement with these targeted searches in terms of, frequencies or redshifts? So is there a particular improvement as a function of redshift here? So this is redshift 0 out to 2.5, which is pretty far. Redshift 1 is about 8 gigaparsecs. That's hugely far. You can see that there's a few points up here that are really improved by a factor of, between 12 and 14 that are nearby. But this isn't really a trend, right? This is just kind of stuff that's, white noisy. There's not a trend there. So there's no overall improvement as a function of redshift. But what about as a function of frequency? I don't really see anything here at all either. So it doesn't seem like there's a particular frequency that's more sensitive to this approach than any other one. What about sky location? Was there a particular part of the sky where you got a better improvement? And it doesn't seem to be the case either. So here we have, the two sources that were the most improved by a factor of about 10, but they don't seem to be preferring one part of the sky to the other. And Rohan and Gondor, right, are in almost opposite parts of the sky. So again, this didn't really give us much of a clue. And then I was wondering, well, these supermassive, if these are supermassive black hole binaries, how do we know that what we're finding with this targeted search approach isn't just the gravitational wave background wearing another mask, right? Because now the gravitational wave background is noise. It's just some sort of red noise that's in your data. And so I plotted Rohan and Gondor on top of this discovery curve for the gravitational wave background and see that they sit right on top of it. And so this is really confusing because it's like, oh, well, then what you're seeing is just residual gravitational wave background noise that sort of is being forced to look like individual sources. But on the other hand, you could say like, well, these individual sources are just contributing to the gravitational wave background and they're exactly where you expect them to be. And so then I didn't really know what to make of this, right? How do you figure out what belongs to the gravitational wave background and what doesn't? And the solution to that is in the paper that I just submitted. Okay, so another thing that we then look for is this thing called the trials factor or the look elsewhere effect. So I alluded to this a few minutes ago, right? So say that you have some sort of false alarm probability for each one of your binaries, right? And if that false alarm is like 1 in 100, but then you look at 100 galaxies, then it's 1, right? You're totally guaranteed to get some sort of false alarm. And so this, I think, was really the nail in the coffin for poor Rohan and Gondor, who if we only looked at Rohan and Gondor, we wouldn't have been penalized by this trials factor. But we were looking all over the place. We were very excited and dedicated to finding the first supermassive black hole binaries. And so what we ended up finding when we corrected for this trials factor was that they are both consistent with noise. So that was, a bit dispiriting, but we learned a lot of things along the way. So we found that on average, the strain sensitivity improved by a factor of 2.6 by using these electromagnetically informed priors. 8 sources had Bayes factors that were greater than 1, which were consistent with what the population models that we have predicted. Rohan and Gondor ended up being really useful test cases for a detection protocol, because before that, we weren't expecting to see anything interesting whatsoever. We were just going to place upper limits on a few of these and move on with our lives. But instead, this turned from a 6-month project into a 2-year project, trying to answer the question, what do we actually need to see to have a detection? What do astronomers, our colleagues, need to see for them to believe that it's true? And we had a rapid response workshop in Santa Barbara trying to address this question. We had another meeting in Aspen trying to address this question. And it's fascinating that actually nobody agrees and nobody knows on what the electromagnetic counterpart should be of these supermassive black hole binaries. And so this was actually really useful to get everyone in the same room and talking to each other, saying, what do you need to believe, astronomers? If there is periodic, how many periods do you need to see? One very famous colleague said 6. Another equally famous colleague said 3 is fine. Everything is fine after 3 periods. And another very famous colleague said, I'll never believe it. And I was like, I don't know what to do, guys. This isn't my thing. Tell me something that's useful. But that was in itself useful. The fact that whatever you see from electromagnetic observations is just shrouded with uncertainty. So we need to come up with really good physics to explain whatever signal that we see. So the trials factors gave us this global false alarm probability. And now what we're trying to do is this big simulations campaign to really establish what the detection thresholds are going to be, right? So we found Bayes factors of 3 and 4. What do we actually need? Is it 100? Is it 1,000? Is it 314? What is the number that we need to see to believe, right? What is the threshold? This is still an open question, which sounds ridiculous, but that's where we are right now. So we're going to follow it up using Nanograv's 20-year data release, which is currently in preparation, and the international pulsar timing array data, which are being combined as we speak. That'll have about 120 pulsars. There's 80 that are already done now. And it should be a factor of 2 or 3 better than the Nanograv 15-year data. So I have 5 minutes left. And I am so happy because I get to tell you a little bit of a secret. And that's that I figured out how to find the correlation functions for the individual binaries. So it took us 15 years to find the Hellings and Downs curve, the blue line that I showed you that the sources average together to give you. Now, that is exciting because we know that only a background of supermassive black hole binaries can create that spatial correlation signature. What I found is that actually individual binaries make their own spatial correlation signatures. And if you move here from left to right, you see the relevant correlation signature for the different parts of the sky. So the correlation function depends on sky location. And so we found that wherever your supermassive black hole binary is on the sky, it creates a completely different correlation function. There are some symmetries which are nice, which we point out in this paper. But now we have something that we can look for. Now we can have something for the individual binaries that says, do we have this spatial correlation function or this equivalent Hellings and Downs curve for the individual binary? This is the smoking gun that we didn't have before that we have now. And just to remind you what it looks like, this is the Hellings and Downs curve here in black. And these are these different fingerprints, as we call them fingerprints, because it tells you a lot of things about the binary. The specific correlation function will tell you where it is on the sky. And in fact, we found that when you do all sky searches, you improve your sky localization by a factor of 3 because each one of these is different, even though some of them are mirror images of each other. So this is going to be the way that we find the first supermassive black hole binaries that everyone believes, because nothing else can make these spatial correlation signatures in your pulsar pairs. Now, because you're a crowd that I think really likes animation, this is the interactive part of the talk, which will go into question time, which then goes into wine. So this is a really good time to take out your phones. So this is another paper that I just submitted, and this is on energetic ceilings. But what this shows is that if you just have simple conservation of energy laws, you can actually predict in a really straightforward way what the biggest amplitude of the gravitational wave background is. You just ask how much mass is there in black holes, and then how much of that mass do you lose in gravitational radiation. In spirals, it's about 2%, and then you add it together, and that's the gravitational wave background. It's really very simple. So if you go to this QR code, I used Claude to make this figure in like a day. It was amazing. It was like, I want to move this label here, and I want to put this over here. And it created this fantastic thing with something called Streamlit. Maybe CCA people know about that. I loved it. It was fantastic. And so now, if you're curious to see what the ceiling is for your favorite gravitational wave background, or what your favorite detector can find, you can scan this little QR code and have a look. It's got like lots of little buttons and knobs and features that are really fun to play with. Okay, so that is the end of my talk. Thank you all for your attention, and I'm happy to take some questions.
Great. Thank you, Chiara. So we have time for questions. Just as a reminder, if you could please use your seat mic when asking a question. So,
I'm not sure I have the right button, but is there an a priori estimate of the frequency of these supermassive black hole mergers? Or do you know that they should be at a certain frequency from mergers of galaxies or some other source?
Yeah, they have a whole lifetime that they go through. So supermassive black holes, before they're gravitationally bound, it doesn't make a lot of sense to talk about their gravitational wave frequency. Typically at about 1 nanohertz, they're...
No, I meant, sorry, how often they should happen.
Oh,
how many are out there? now in
Sure.
the sky?
So yeah, the merger rates are something like 10 per year.
Okay.
Yeah. So it's not surprising to find some. It's up to you to tell people what to talk.
Lovely talk. I was curious if you could talk a bit about the physics that goes into that simulation of the electromagnetic counterparts and why you expect that periodicity.
Wow. Okay. Well, that is a more difficult question. So this is an MHD simulation. And so what happens is that you have the two black holes that are interacting with each other and with the circumbinary accretion disk. Maybe I should go back and throw it up because it's nice for everyone to look at. I'm always really envious of my simulators talks because this is every slide for them. So these two black holes right now would be in something like, they're in an in-spiral phase. And so the in-spiral is this very slowly evolving phase. So they could spend something like 50,000 years in this phase where they're exchanging gas back and forth. And you can sort of see that there's this interaction between the binaries themselves as they're like throwing gas between each other. And then also that gas will hit the wall. And it hits the wall in a specific place. So there's this cavity that's been cleared out by the black holes, but they're also shooting gas. You can see here as it shocks the wall. So depending on the eccentricity of the binary, how elliptical the orbit is, and what the mass ratio of the binary is, if they're 5 to 1 or 1 to 1 or 10 to 1, the gas will hit the wall in a different place. And so these binary orbits might be in a 1 to 1 orbit with the lump of gas that forms, or it could be up to 5 to 1 or 6 to 1, depending on if they're circular or if they're eccentric. I'm not really sure of the level of detail you're going for, but I'm happy to talk to you about it more after.
This works. Got it? Okay. So I'm not an expert in this, but it just seems to me that is very, 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 very precisely. And my question is, how do you know that you can?
Oh, what an excellent question. This is really the perfect question. So these millisecond pulsars we time to better than 100 nanoseconds in some cases, but not all cases, right? And as I was describing earlier in this animation, there can be a lot of noise in the interstellar medium. There can be clouds of gas that come between you and this radio wave. And if you've studied any kind of astronomy, then you'll know that the lower frequency waves are delayed more than the higher frequency waves. And what's a time delay when you're looking for gravitational waves? It's the same thing. So then how can you tell the difference between this gas delay and a gravitational wave? Well, the answer is this Hellings and Downs curve, right? So this is a spatial correlation function that's completely independent of the pulsar timing itself. Now, when you're looking for the gravitational wave signal, you're actually looking for two things. The first thing that you're looking for is this correlation function, and this only depends on the geometry of your pulsars. So what this tells you is that if pulsars are separated by a small amount, they'll have a strong positive correlation, which means that their timing residuals arrive early and late in phase like this. When they're anti-correlated down here, close to 90 degrees, that just means that one arrives early and the other one arrives late. So that's what the minus sign means in this case. So this tells you about a modulation that happens to the overall amplitude as a function of the angle that separates the pulsars. Now this is a purely mathematical geometric expression from general relativity. Nothing about timing noise or anything goes into that. That's right. This is with plus and cross polarizations, but if you're interested in beyond general relativity, you can add in breathing modes and all sorts of fun stuff. Yeah, and so, but this is how we know that there's a gravitational wave background, because if we were just looking for the amplitude of this red noise, that could be anything, right? So you can't only trust that. You have to look for these two things at the same time. That's why.
mind-blowing and fantastic, and I'm a layman, and I wish there were more talks like this.
Thank you. I don't know if there could be any higher praise.
So as a layman, can you talk a little bit about time? I'm wondering what you said about 10,000s of years of rumbling before the merger. How
Yeah.
much of that is because of relativistic effects, and that from the point of view of the black hole, it's actually only 10 seconds? I mean, is there any aspect of that?
So, I mean, so you just asked me about special relativity and general relativity in a nutshell, which is awesome. I'm going to do my best to answer you very quickly. So, okay, so number one, the fact that there's ripples in the fabric of space-time is from general relativity. And so that's because we can model space-time as this, fabric that we live in, and the curvature of space-time is gravity itself. So gravitational wave is this ripple in the fabric of space-time that's propagating at the speed of light. And so the amplitude of those waves tells you how big the things that made them were. So supermassive black holes that are 1 billion or 10 billion times the mass of the sun can create the most massive gravitational waves because they're so big. They can really cause they're kind of like whales jumping in the ocean, and they can create really big waves. And what LIGO sees are much, much smaller. So that's like, little tiny ripples on the surface of a pond. The ones that we're looking for are 1 million times larger, or that we found, I should say. So, and then when you're talking about the time delay effects, remember that these are also relative. So if we go back to the movie Interstellar, right? If you're on like the water world, that was a really good example, where you're in a really strong gravitational field and you're on the surface and you think everything is fine, but if someone far away is looking at you, for you, it looks like, you're going in super slow motion. And so for you as in you on the spaceship. So those kind of effects are always in play. But remember that they're always just relative. There's no kind of absolute time that we can think of. It's always relative between the observer and then the person who's, falling into a black hole or doing something else very dramatic.
Hi, I have a question about the paper you were showing where we can see the curve of different supermassive black hole depending on the sky location.
Yeah.
How does the shape change based on mass ratio, eccentricity, and edge on or face on and other things?
Oh my goodness, you're such a pro. That's an amazing question. Okay, so number one, the cosine of the inclination angle is folded into the amplitude in this kind of formalism, so it doesn't affect this at all. Okay. Eccentricity just means that you're redistributing the power to different harmonics. So that's a function of frequency. And these are purely geometric. And so eccentricity doesn't affect it. Also, most of the binaries that we're finding or that we expect to find would have kind of weak eccentricity. But still, this is a purely geometric effect. But I know why you'd be interested in eccentricity.
And mass ratio?
And the mass ratio, again, the mass ratio goes into the amplitude, right? So this triangle is like the chirp mass to the 5/3. But this is in the correlation function. And so here it doesn't matter at all. This is a purely geometric term.
So you're saying the shape is totally dependent only on location?
Exactly.
Okay, that's cool.
Exactly, on location, and that there's gravitational waves. And this is, again, using plus and cross polarizations. But you can also do tests of GR using these curves.
One more. We have time for one more.
Howdy. So in one of your very first slides when you were talking about supermassive black holes and the timeline of the universe, you mentioned that the timeframes in which they had to start big because there hasn't been enough time.
Yeah.
Was that meant to imply do we know enough about the very early universe to establish a lower bound at which black holes, supermassive black holes, could have started to form? Like, could they have been there from, 1 year after the beginning of the universe? Or do we know much about that kind of bounds?
Well, we know that there's the cosmic microwave background radiation. And that gets you a few 100,000 years to after the Big Bang, where everything was like in this kind of liquid, goopy form. And even the photons were coupled into this liquid goop that eventually cooled off enough to give you the CMB photons. So that's an ultimate limit, I suppose. But I don't know. So yes and no. So I can take your question and say no, but I could also say yes. So I'm going to say both. So right after the Big Bang, there were quantum fluctuations that at the time were very small. But then inflation happened. And so those quantum fluctuations could have been blown up to be the size of the universe. And so this is a source of primordial gravitational waves. Now, for them to be detectable, you would have to have a cosmology where you have bouncing universes. It has a cool name. It's called ekpyrosis. And I've asked Nico how, what this means in Greek, and I haven't gotten a clear answer yet. I know, every time I'm stumping you. But anyhow, someone came up with the name, and it's very cool. I think it's from Paul Steinhardt's group at Princeton. But anyhow, it means that you have a bang and a crunch, and you have the cyclic universe that goes back and forth. And that's the only kind of universe that could give you a signal that has these kinds of quantum fluctuations that you'd be able to detect today. So yes and no. So it's a very exotic kind of physics, but it's completely, well thought out. It's not crazy. It's just something that's not standard and not in the current zeitgeist. And so with the formation of primordial black holes from the early universe, those could have been formed from, again, these kind of fluctuations that were somehow very overdense and apart, where you created this patch of space-time that curled in on itself and created a singularity, and then you have a primordial black hole. There is a lower bound on those. So when those eventually evaporate, we expect them to create a burst of radio waves. Martin Rees showed this in the 70s. And when we started finding fast radio bursts, people thought they might be these primordial black holes that are evaporating. Either way, whether or not you believe that that's the source of the fast radio bursts, there's the black hole evaporation timescale that tells you how massive a black hole can be today if it formed at the beginning of the universe. But yeah, it's a good question. And the fact that there's new evidence for these little red dots being early supermassive black holes is exciting. It tells you about the seeds of the black holes, but not necessarily that they're the only seeds. So it'll be really interesting to see how this plays out. It's very much at the forefront of research today.
All right. Thank you for joining us. We look forward to seeing you at future presidential lectures, and let's thank Chiara one last time.